welcome back to the stream. We're getting things started. This will be another stream on that kind of internet-connected camera that we've been looking at a few times, the D-Link DCS-933L. This time we're going to take a closer look at that USB connection that we noticed in between the camera chip and the kind of regular system on chip there that runs Linux. Oh, nice. I was about to try to announce the stream on chat, but as usual, other people are going to beat me to it. There's always so much other stuff that I've got to be turning on when I'm actually starting the stream around here. I've got to automate stuff if it's going to happen. So welcome back, everyone. We have cat still. Let's switch to the cat camera. So this is still in the middle of a kind of work-in-progress tornado related to racking all of my streaming equipment. But Tuco's already enjoying the warmness up here. There we go. We have the star of the show, Tuco the cat, enjoying the warmest seat in the house right above the audio interface and all the rest of the video hardware. So this project is mostly going to be pretty straightforward. The thing that makes this difficult at all, normally if you had two USB devices, you could use some off-the-shelf tools to get in between them. So we have USB analyzers. I've got this Beagle USB 480 that I'll be using. But the thing that's tricky here is that we don't actually have physical USB ports, since these are devices that just hang out right next to each other on the same circuit board. And the only reason you can tell that there's USB really is if you take the software view, you can see that from Linux's perspective, there's a USB device representing the entire camera. And then on the circuit board, you don't really have direct access to the pins. It's all ball grid array, and I haven't found pinouts for these parts. But you can see this, this pair of length-matched traces that seem like they might be USB. And so on a previous stream where we were just poking around on that circuit board, we scraped off the solder mask on those traces and verified with the oscilloscope that that is indeed USB traffic. Anyway, I'll try to put the camera down and stop making everyone seasick. Maybe since this is on a tripod, I can actually extend the legs so that it can keep up with Tuco's tallness attribute here. Granted, this is no match for the tallness attribute of a camera robot on wires, but that's still a work in progress. There we go. Yeah, he really likes it up there. It's only been set up for a couple days now, but the thing that's right under where he's laying is the audio interface, which runs really hot. Like, I don't know why it runs. Like, I mean, I don't think it's broken. I think it's just designed to run pretty hot. It doesn't have any real cooling to speak of. So I stuck it at the top so it wouldn't warm up anything else, really. Yeah, the matrix scanning on the VFD sure is visible on this camera. It doesn't flicker at all in real life, as you would expect, but I think that's mostly the PWM from dimming, but you're probably also seeing some of the column-by-column multiplexing that it does. Aw, Tuco's gonna keep being the cutest little creature. Yeah, he gets really affectionate when he's just hanging out on the rack. Like, I think he really likes the warmth. I'm curious how much power this is actually drawing right now. I don't think I could read the front of, oh, maybe I can. I think the UPS says it's at 20% capacity, which probably means about 400 watts. this cat. Okay, this won't be an entirely cat stream, but I figured this is too good of a cat moment to pass up. He is so purring right now. Those things on the laptop stand in the back are some knobs and buttons, which I figure will be pretty important to have control over the audio, because if something goes horribly wrong and something's really loud, it would at least be nice to have some mute buttons and some volume controls handy. So that seemed like something that should always be attached to the rack, even if other things are kind of hectic. And then there are some radio receivers for the wireless camera and the wireless microphone, since the box, the rack actually is pretty well grounded, so it's very bad for radio signals. Like the Bluetooth on my Mac in there does not work at all, so I've been having to adjust the way I have input using an external Bluetooth dongle and whatever else I can manage. Yeah, this is a good Tuco moment. So the chip in this camera, I think, was an OV780. The marking on the chip was something like OV00780, but then the tool that controls it in Linux is called OV780. So I think that's the name of the chip. There's also a firmware loading step during boot. There's a firmware binary hanging out in the file system. So that might be fun too. I don't even know what architecture to expect on that chip, but I mean, I haven't taken a look at the firmware yet, but it could be interesting. I don't really know what I would expect to be able to do from inside the camera controller firmware. Like, would that actually be responsible for like DSP algorithms for doing JPEG compression, or would that just be a little microcontroller that sets up the data paths? Not quite sure. Because it could just be a microcontroller that's responsible for speaking the USB protocol bits, but I suspect it would probably be on the imaging path somewhere at least. All right, well, maybe Tuco is giving us the sign that it's maybe time for desk time. Clearly the rack should just have a built-in Tuco cam, but I mean, I think the flying one will be better than that particular option. Oh, Arsenio Dev in chat is asking what new USB knob controller is that on the laptop stand. That is the launch control, the Novation launch control. I have that one and the Matrix one that goes with it, the launch pad. And the launch pad is super handy for just like fussing around in Ableton, so I'll probably want that on my desk. But this one seems like more of a general kind of like streaming control room object. And at least the way I use Ableton on its own, I don't need something like this as much. But since I also run my streams with Ableton, then having something like that that gives me control over a bunch of the audio channels has actually been kind of nice. But it still isn't really completely hooked up. Like, I want to make sure all the channels are useful and then label them and stuff like that. Yeah, I like Piotr's comment, if you can't follow a cat, give the cat a warm spot. Yeah, really, if I wasn't already planning on the robotic Tuco camera, then having a Tuco camera that just always points at the top of the rack is probably a pretty good compromise. There might be something I can do with the on-screen controls for the camera to make the flickering better, but I'm not going to worry about that right away. Let's take a look at this camera. Welcome back, everyone. This was just something I was using to test the microscope. I've still got that wad of cable salad back there, and this rack is not totally set up, but I have microscope recording now, at least, or at least microscope streaming. I don't have the offline recording stuff set up anymore, or currently. That's still something I need to re-set up. But we can stream in the microscope. So these are the cameras, our old buddies. These, just for reference here, let me show where you would find those. Since they are currently recent on Vimeo, but if you're watching this stream in the future, these might not be the most recent, so you might have to go back and search for them. But if you look at the Sanrio Labs Vimeo page, this archives all the Sanrio Labs streams. And a couple of the recent ones actually were about this particular camera. So we had, I think the first one actually was, see all, that seems useful. Yeah. Yeah, this was the first place we saw them. So this IoT webcam serial prep. There, I just opened up a bunch of these, just a big pile of them, like 30 of them, in order to add a serial breakout header for these cameras for the class that Sanrio ran. So this was our first introduction. I just kind of poked around in the shell, but we were mostly just tasked with adding headers on a lot of them here. And so this was a really long stream. What was that, 10 hours? Yeah. Oh no, this is 10 minutes. Sorry, no, this is not the stream. This is the condensed video. There was a stream of this previously, or at least I streamed some of it. Maybe that's my imagination. Maybe I did not stream that work. Or maybe I'm just missing it from the archive. Okay, well, regardless of what format the video is in, I thought there might have been a stream of this also, but in any case, this particular job was the first time we saw this camera. We poked around on it, but then we took a closer look at it more recently. So here this is probably going to be most relevant to today's work. So here we were just taking a closer look at the circuit board and exploring what's connected to what inside it. And then we also just went through a couple of different techniques for extracting the firmware from the little SPI memory chip on there. Did I draw a nice little DaveCAD drawing in this one? So yeah, here we were taking a look at a lot of the interconnections. At some point in here, we actually start scraping off the USB pads. This is still looking at flash. Hey, Tuco. That's the USB. Hey, Tuco. I hear you. You're not up on the rock anymore. Tico, do you want to play Bolt? Oh, Tuco, you're so warm. So this is what we did previously, just exposing this just to test whether it was actually USB, and then I think we took a look at it on the scope, and that was the USB data. So at this point, there was the option to go one step further and, okay, we know this is USB. We can see this device from the software side by just going into the Linux shell and looking at, proc bus USB devices, and we can see the device there. We can see the binary that's talking to it. So we could reverse engineer it from that end. But there's also a hardware approach available now where we could just cut this trace and actually attach different devices to each end. So that opened up a bunch of possibilities. We could attach a USB analyzer to kind of semi-passively monitor the traffic that's going back and forth. We could attach just any computer that we want up to the camera chip and then just interact with the camera chip directly. We could attach our own devices to the system on chip, which could be anything we want. So that could be a way to attach USB storage for getting data into and out of the device more quickly. Could be a way of attaching, additional serial ports or that kind of thing. Around. Oh, that's a good suggestion from Arsenio Dev to track Tuco using an IR camera like on the Wii. Yeah, that's certainly possible. If I wanted Tuco to wear a collar all the time or during streams, then I could certainly put like a retro reflector on the collar and use modulated IR to track that. But I think my goal here is to do something that doesn't require him to always wear a collar. He wears that one with the little Bluetooth tag when he goes out into the hallway, but when he's just hanging out here in the shop, I don't like to have him wear something all the time. Hey Tuco, what do you want? If you bring me a bolt, I will throw it for you. That is the standing deal here. But you're just going to rub up against me, which is also cool. But that doesn't mean you get a bolt. I think he's looking for one, though. Rawr. All right, so I think the most useful thing, honestly, would be to, like, sharp cat. So I think the most useful thing to do would be to epoxy on to the board a set of like a USB Type A and Type B connector, so you can just attach it to external USB devices. To do that, I first want to know which one of these is D plus and which one of them is D minus, since we don't have pinouts for either side. There are two ways I can think of to make that determination. One of those is to look at the signals with the oscilloscope. The other is to just try both and see which one works. So the second strategy, just trying both, seems totally fine. Like, that doesn't seem likely to damage things. It seems likely to work. But since I happen to have the scope here, and I think that would make a nice demo, I think we're going to try just examining the state of the D plus and D minus that way. If you happen to have a device which is not high speed, but is low speed or full speed, so 12 megabits or 1.5 megabits, then you just need a voltmeter. But for high-speed devices, they idle at a state where both of the wires are near 0 volts, so you can't really tell without using an oscilloscope or making an educated or uneducated guess and just trying something. So let's take a look at what we've got here and maybe try some experiments. Also, I don't think I need the headphones right now. I was just checking out the audio. It always feels a little weird, like hearing myself talk in the headphones. Oh, where's the cat? Oh, there he is. Okay, so let's get this camera opened again. So I think we'll need to yet again take the serial port off of this, since it's easiest to deal with this not having the serial port attached to this case. Although maybe I'm lying, maybe... Yeah, I think we're going to have to maybe make this... It's probably good at this point to just permanently choose to not have the top of this case on and not use this serial port attachment, because then we can start epoxying larger things to the circuit board. As it is right now, this thing was convenient to just like have a bunch of cameras around for experiments and for workshops and stuff, and to still be able to fit them in the original case. But at this point, I think we're better off not having the back case on here at all. So let's just desolder this. This is our old friend. And I'm just going to use a big soldering iron tip. So we probably will want these back, because this is really our main way of interacting with the system. But I think we're going to end up wanting to put these back on some headers that are actually mounted to the board, so that we have something mechanically less unstable to deal with. So that's desoldered. And now we can just start taking this apart again. Okay, so at this point there's only one screw holding this down to the front side of the case. There's also another circuit board here with the infrared filter that we need to worry about somewhat. I don't think we need to actually take this off, so instead of actually taking this off, I'm going to reinforce it slightly with some Kapton tape. Because right now the board's a little wobbly. You could use other things. Kapton tape is nice for this because it won't melt when we're soldering nearby. So I'm just going to cover up a good amount of this, and we can cut holes in it later if we need to, but... And then I don't want to cover the camera lens. I don't really care about covering the microphone and the IR LEDs with this. I'm just going to angle it over that way. This will be easy to take off if we need to, but this will just keep the board secured while we're working on it a little bit. Okay, and now we can give ourselves a serial port again by just attaching a header here. We can use this ground. This looks like it was designed for an optional RF can that they decided they didn't need, but we can use that as a convenient mechanical anchor for some headers. So we can give ourselves a strip of headers with some grounds and then also attach some headers over here. So that might be the next step, just kind of get back to where we were with debugging. But then we want to attach some connectors to, so here's that USB line that we were looking at before. So we want to attach some connectors there. We want two connectors, kind of a USB type A, so the kind that you would usually find like on your laptop. We'll want one of those on the system on chip side to attach a device to. So for that we need this D plus and D minus. We also might want to find a plus 5 volts, or for perhaps more safety we could supply the 5 volts externally. But the connector itself will want to have 5 volts on it somewhere. And then of course ground, but we've got ground handy. Then on the camera side, we'll want to do something similar, but this time we can attach a USB type B connector, so the kind you'd find on like a printer. Hey Tuco. And with that connector we can just ignore the 5 volt power, since this will be getting powered by the circuitry here. And we just have to attach D plus and D minus. But for either of those, it would really help if we know which of these is D plus and D minus. So let's just do an experiment and make sure that we know how to do that determination first. So I'm going to attend to the cat first, because he seems like he wants to play. But then let's do an experiment using the Raspberry Pi so that we know how to tell D plus from D minus under these circumstances. Hey Tuca, what do you want? Do you have a volt? Tuco? Show me what you got, little guy. Hey Tuco. You are so warm. I don't know where your toy is, too. Is that your problem, too? You're so chubby. Wow, I don't see a bolt. Tuco, keep looking. Is that the noise you make when you're frustrated, Tuco? That sounds similar to some noises I've heard him make when he's like about to try jumping somewhere ill-advised, and he knows it's ill-advised, but he doesn't see a better way to get there. Yeah, he's looking for a bolt. I'm sure he'll find one. Okay, so first step, multimeter, voltmeter mode. Let's also just have a USB pinout up here for reference, just so that we're all on the same page about which thing is which. So this is what we're dealing with. So in this diagram is looking at the plug. So this, you can see it's kind of illustrating the plug itself, and you can see that the ground is the longest, power is almost as long, and then D plus and D minus connect last. So got this little doodad, which I think is kind of useful. It's a USB Type A male and a USB Type A female connector soldered to each other so that we can probe the signals going between them. So if we hold this the same way the diagram says, then we have ground on the left, then D+, D-, and positive 5. So now with it plugged into the Raspberry Pi, now reading from the top, it should be ground, D+, D-, then +5. So let's write that down just so that it's easy to remember. My hugely disorganized shop. I don't know where my pile of Dave CAD went. Here's one. My Dave CAD user interface frame factory instance. So we have 4 pins. 1, 2, 3, 4. And this should be ground, 5 volts, and then in between D+, D-. So let's verify this with voltmeter. So I'm just going to get a ground reference from over here, and then can I get this in the frame too? Okay, so here if we take a look at top, 0 volts, 0, 0, and 4.65, which is what's passing for 5 volts right now, which is probably just the USB power supply I have this plugged into, and all the voltage drop in between. So then, let's try plugging in a USB memory stick. You can see its LED blinking away. And if we take a look at this, we've got also 4.5 volts, which is close enough to 5. Then about 0 volts and 0 volts. So that's not very helpful for identifying them. It turns out that's actually a change that was made in high-speed USB, so what most people think of as USB 2 speeds, so 480 megabits. It uses a mode where when the line is idle, it actually hangs out in a state where both wires are near 0 volts. That wasn't always the case, and if you plug in a slower device, like say a USB keyboard, then you'll actually see them go into, I think, what's called the J state, if I'm remembering right, which is one of the two differential states. So, do I have... Let's reboot this Raspberry Pi. I was suspicious of why the caps lock light wasn't working. Maybe the caps lock light just doesn't work on this. So I've got a keyboard plugged in now. 4.5 volts there. Then D+, 0, D-, 2.89 volts, and kind of jittering a little bit. So there's going to be traffic on any USB connection that's idle unless it's asleep. But here we're seeing that the idle state is definitely not, both lines 0. The idle state seems to be D+ at 0 and D- at close to 3.3 volts. So that would be a great way to identify which one's which if we already had a connection with a working, full speed or low speed device. But in high speed mode, we've actually got to look at the packet structure. So let's do that next with the USB memory stick. So I currently am missing some of the parts that I need to get the scope video capture back on the stream. but for the moment we can just point the camera at the scope like regular people. So I think we're done with the meter right now. We have bonus cat here. Okay, I think I've got 2 scope probes in this terrible desk mess here. So this, again, is something that will only work if you have a pretty high-speed scope. So it's certainly acceptable to just try both. Try it one way. If it doesn't work, try the other way without really being able to see the signals. 'Cause otherwise, without having a scope that actually can see the high-speed signal, I'm not really sure how to do it. But like I said, this is optional, and I just figured it'd be worth doing since we have the equipment here. You can actually take a look at what the signals look like. Okay, I'm going to see if I can get away with using the ground alligator clip. I don't know if the ground alligator clip is going to be sufficient, but we'll see if it'll work. So I'm going to hook the yellow wire up to D+ after I ground it. And am I going to have enough room for both grounds? I think I'll have to daisy chain them. Okay. I think those are both on the place they're supposed to go without either of them shorting to VBus. Alright, and these will both set to the same volt per division. Alright, so that's both traces. You just can't actually see them yet. Let's try plugging in a USB memory stick. Cool, let's get a closer look at that. That is our USB 2. Looking a little bit gross, but I might blame the ground alligator clip for that. So that thing that's moving around and looking kind of like a squid or something, I think that's the frame number changing in the start of frame packets. So I think the easiest way to identify which line is D+ and D- is going to be in looking at the end of a packet. So at the beginning of the packet, you see this alternating pattern for sync. Then there's a token. Hey, Tuco. There's a token, there's the data, Then here's the end of packet, and you can see how there's this stable state where that's green on top. So what did we actually connect green to? So green is D minus. So that's the J state. That's the same kind of idle state that we saw before on low speed and full speed. It's just that with high speed, it doesn't maintain indefinitely. It just holds on for the length of the end of packet, and then it shuts off. And then at the end, here, when everything goes back to 0, that's when the drivers are actually shutting off. So it's no longer actually driving current onto the lines. So, wait, is that alternating? Let's make sure we have consistency here. Oh, it's alternating. Maybe I lied. Maybe that actually is not the J state. Maybe that's after NRZI encoding. Okay, so yeah, that was my mistake. So the end of packet is, I think it's a sequence of like 0, 1, 1, 1, 1, 1, 1, 1, etc., or something like that. And so if I remember right, in this encoding, a 0 is an alternating bit. So if you encode a run of zeros, you get like a square wave. If you encode a run of ones, then you get a steady state. But then there's a bit stuffing operation that prevents that from carrying on too long. So if there's too many ones, then it inserts a 0. But yeah, so that polarity is not reliable. I mean, the encodings are so similar. I'm actually curious what I'm not actually sure what actually breaks first when you connect USB with D plus and D minus swapped on a high-speed device. Because I know, I mean, for full speed and low speed, it would fail as soon as it tries to detect the speed, because the speed detection uses USB D plus and D minus for that. But on high speed, I'm not really sure what would break first. Catching up on chat slightly. Oh, so Mikkel Jeppesen, yeah, I worked on USB pass-through. I joined there when, that was like 2005, so we didn't really have, like USB 3 wasn't there at all yet. USB 2 was there, but was new, and like a lot of devices didn't really work at all in USB 2. I spent a lot of time basically trying to make USB webcams work. Like I implemented isochronous in EHCI, and I implemented the XHCI emulation and the macOS backend, and did a bunch of that kind of stuff. I wrote vmioplug.kext, so you can send me all the hate mail related to that, but please don't. So, okay, this is proving to be a little less intuitive than I was expecting. Let's get a little bit of help from the USB decoder on this scope. So the decoder on this scope actually doesn't even want both signals. It's just looking at one. I wonder what that reserved indication is. So these are the start of frames that we would expect. It's usually leading with a yellow. So the yellow, I think, what was it, D plus in this case. So the very first pulse there is D plus going high. But here it's the opposite. And this is an in token, so I think that might be related to the D plus, or sorry, the data 0 and data 1 toggle. Also, the signal quality here is pretty bad, assuming that's because of my ground alligator clip. Well, we might have to look at the sync packet instead of the end. So the sync would be this section here. So it starts out with this high frequency kind of alternating states, J and K. And then you see these longer runs of ones and zeros are the beginning of the synchronization part of the packet. Let's see if these are consistent in the polarity. This is one of those things where like I could spend all afternoon trying to read the USB spec and interpret whether this part of the packet has consistent polarity, or I could just take a look at it and have a pretty good idea of what's going on. Yeah, I think this is what we want. So that first pulse in the sync packet should have green on top, which means that D plus is low and D minus is high. So let's take a look at the traffic we've got on the camera and try to make a similar determination there. Let's write down what we've got so far here. So hey, Stuke. So got that squiggly sync pulse, then the first pulse in the, I think that's the PID, so like the part of the packet that tells us what kind of packet it is. So that would be the first run of bits in there. So that'll be an easy way to tell which one's D plus and D minus, assuming we have a fast enough scope. So let's try that. Hey Tuco, what do you want, little cat? Do you want to yawn? All right, so let's get the camera set up here. I hear you, Took. And I'm gonna want a serial port, but let's just start up without the serial port and figure out which pin is which, and then we can just do all the soldering. So for that, I want one of these plugs. Oh, power supply. So 5 volts at 1 amp. Power on. Now I should just be able to dig in. Sorry, Took, gotta borrow your camera. Alright, so I'm just gonna be probing one of these at a time, I think. And let's ditch the alligator clip thing. Use the spring clip since we've got a convenient ground nearby, and we're going to be probing one at a time. That is the little IR shutter clicking. How did our chat get wedged again? Fix that. Oh, maybe Tuco's just hungry. Yeah, I don't know, maybe. Do you want to play, or are you hungry, Tuco? That's usually what he does when he wants to play, but it could be either, I admit. This is a job for the microscope, I think. See how much cleaner that is with a proper ground? So that's the sink at the left, then we have the PID, which in this case, yeah, this looks like this is D+. And it looks like this is D-. Did you catch that? Let me write this down, and then I can do it again with the scope screen large. D+, D-. Let's take a look at that again, a bit bigger. Okay, so I'm getting the probe positioned. That's the line on the left. So it starts with the sink pulse train, then we have the PID that indicates what kind of packet it is, and then we actually have the frame number counting away. And the part that I'm looking at to differentiate D+ from D- is the polarity of that first run of more than one bit after the kind of square wave train at the beginning. So that would be the first couple of bits in the packet's PID. So it's packet ID. So in this case, that being low, according to my notes here, which come from observing the known signals before, and that's a little bit quicker than trawling through the spec sometimes. So according to my notes, that would mean if that's low, then this is D+. Then if I point the probe over at the rightmost trace, that was the left one before. So here's the right trace, then you see something very similar, but the polarity is different. So that run that we were looking at now is high, which means that's D-. So I think that's what we needed. I think now we can do some soldering. Let's unplug this. Hey, Tuco. Let's see if Tuco needs food. Hey, Tuco, what do you want? So I think the next step here is just to give ourselves some connectors to work with. I'm thinking combination of headers for the serial, and then USB Type A and Type B for the USB. So here's our header, and one USB connector. Here's another USB stuff. And another USB connector. Let's put this flash stick back together. All right. First of all, let's see how well this lines up with the header positions we need. Looks like a 0.05 pitch, so twice the density of this header. Maybe it's worth using a dual row then. I could use a little piece of something like this. And I have room for a bunch of grounds on the right side, but then room for additional wiring if anybody wants it on top. So oh, yeah, there's some suggestions in chat about like small and large connectors, I think. Yeah, I probably do have some smaller connectors, but I've got a bunch of these and these are handy. Let's see where I need to solder this from first. Let's also turn on the soldering iron. I think I've just got to attach this blob over here. That blob might want some flux. How close is that? Pretty close in those axes. It needs a bit of a tilt that way. Okay, I think I've iteratively squidged it over to exactly where I want it to be. We can solder those in place and then clean up the ground connections. I wonder if I can use this ground to physically attach the USB connectors to. I was assuming I'd have to epoxy them, but this would be nice to have in addition to or instead of the epoxy. That tricky little ground plane. I'm gonna actually have to use some braid to get that off again. It's very easy for solder to stick right there when I don't want it to. Hey Tuco, I feel you on my legs. Did you like the dinner? Okay. Ow. Let's touch the thing I'm soldering, that'll help. Just trying to move it more into view. Okay, let's get another microscope angle on there. Is that good enough? So that'll be some grounds and some mechanical anchoring. Then we have those two, and then we'll run some magnet wire for the other two. Magnet wire. Actually, let's use some Kynar wire. That might be a little easier for this. And it's right here. Just going to make two really little pieces of this. Probably still going to be way too big, but it's fine. I will be switching to a smaller soldering tip, just not quite yet. For this, I don't really need it, and I still want to solder the USB connectors to a good ground, which will require more heat. Oh, I'm pushing it further away. That isn't helping. That looks somewhat shorted. That ground plane pin, man. It's just not my friend today. Using the desolder braid on the ground plane is just all about waiting for it to heat up. Ground plane. Could also be the flux is all burned up in this part of the desoldering braid, but it seems like more of a heat problem. Oh, I didn't lift a pad, did I? That looks suspicious. I think it's just dirty. Let's get a fresh snippet of braid to use there. Okay, that helped. I guess that braid was just more saturated than it looked. Can I solder this stuff back? Oh jeez. I was like, had my elbow on the keyboard and it was on Google image search, so it's like flipping through images like some bad sci-fi movie. Okay. Now I'm going to try to just stick that wire, or perhaps even a shorter wire on there. I could also just skip that since I have plenty of ground. It's just kind of doing this for completeness, but... Yeah, you know what? I'm going to skip that. There's plenty of ground. Let's just do this 30 gauge wire and move on. So that's fine. And actually, I guess I might as well use this pin. If I'm giving myself a totally weird pin out, I might as well just use one that's convenient here. That would be easier if I wasn't also holding the soldering iron. Okay, just a little dab of solder there. Okay, tiny bit of collateral modification, but I don't think any damage. Okay, so we should have a serial port. Let's look for where the USB connectors can hang out. So they should be in this general area. Ideally, so this trace is going off to the camera chip, I think is right under this. So somewhere along here, maybe even on this side would be a good place for the USB Type B. So like the kind of printer style connector. And then over here, closer to the system on chip, might be a good place for the USB Type A, so like the same connector you'd find on any other computer. So then one question is, if we had a USB Type A, which way would we want to orient it so the traces line up with the D plus and the D minus? So here's the connector we would have. And if we take a look at what we've actually got here, now I'm just looking for a pin out so I can remind myself which one is actually which. Man, so much of electronics is just remembering which pin is which is something I'm actually really bad at. We have ground, D plus, D minus. So I think we want this to be oriented kind of like this. So if we looked at the wider view, so we want these two traces to be in this orientation. So where I'm basing that off of is my little diagram here. That's those two traces with D plus on the left, D minus on the right. And this connector actually matches this pin out if you're looking at it from the bottom. So we have ground, D plus, D minus, 5 volts. So then, oh, is that right? I think I might have just talked myself into a slightly different answer, because that actually would be this orientation. Okay, maybe that is right. Let's find a second opinion on this pin out just to make sure this is going to be correct. So this would be 1. Okay, maybe I did have it right the first time. 1, 2, 3, 4. 2 t minus. Oh no, yeah, my second one was right. So let's just go over this together. So this is a type A female connector, so it's the one they have listed as device type A on the right. So if we're looking at it from the front, we have VCC, D minus, D plus, and ground. And then D minus, D plus, and ground. So oriented like this. And then we'd want power coming in over here, and then this connects to any convenient ground plane. Whoops. So we could put that any number of places. Ideally, I'd want to not have to run the D plus and D minus wires any longer than I have to, because we're dealing with pretty high speeds here, and signal integrity will sneak up on you. So I'm thinking maybe something where I can anchor the ground pin right there to the ground plane, run small wires for those two. I could also give myself a closer ground plane so those actually line up. Something around there, maybe. Oh, there's actually that. So if I just angle this, maybe. Let me bend these legs down. They're a metal case, which looks very easy to short these legs out on if you just go bending them willy-nilly. So I'll attach the shield to the ground plane too, why not, just for mechanical stability. Then those get really close to the traces. I could even potentially maybe get them to touch if I'm really lucky. Right now I'm mostly just looking for a mechanical spot, since I think this is kind of a place I can have the connector hang out. This is kind of hanging off the edge of the board a little bit. So maybe if I just finish kind of bending the leads into position, and then start to solder the parts that are mechanically important. You can also get an impression for just how many opportunities there are for getting the signals backwards. So even if you do look at it on the scope, you might just get it backwards and end up having to try the other orientation. I'm basically turning this into a surface mount jack, because the surface mount jack is kind of what I wanted, but this is what I had. So I could solder that on. Yeah, and then run a wire to to VUSB, and then have those hang out there. This is seeming viable. I think what I'll do then is I don't want to have like a stub, like a transmission line stub here. I want to make sure that I cut these lines right where I join them to the plug. But then I'll have an unused section of these traces kind of going along here. And then over on this side of the board, I think right around here is a good place to mount the other USB connector. And then I'll tap in around here. So I think that's what I'm going to do. And because of that, I don't need to trim that yet, since I'll trim it when I know exactly where to do so. But first I just need to mount this somewhere. So I'm just trying to mount this so that it's both kind of convenient and also that I can get these as close as possible with the traces, as close as reasonably convenient. So I think I want something roughly like that. So I'm going to stick some blue tack there to hold it in place, and then solder one of the ground tabs. Hey Tuco, what do you want, little dude? You done with your dinner? I'm not going to try to make this a really good joint because the blue tack isn't going to hold too well, but I just want to tack this a little bit and then verify everything else. That looks cool. I don't think that's shorting out yet, but that makes me really nervous. The power and ground both get really close to that metal shield when I bend them that way. Power I'm going to be supplying externally, I think. That looks fine. Let's just tack the other side. Connector is hot enough, but the board is still heating up. I think that'll be structural enough. It's not pretty, but let's do something similar on this side and then test it a little bit. It's not necessarily ideal to connect the shield directly to ground like this, but it's not terrible for a setup like this, and it'll help with the mechanical anchoring. So I think right there we're going to see our actual ground plane. I hear you, little dude. Whoa, what a jump. So I think what we want to do is just scrape away the solder mask there and attach this. That's still really warm. Why did I put my finger on that? Oh, that makes me feel slightly better. I pushed it under a little bit. But yeah, let's do that scraping of the ground plane solder mask. Careful, Tuco. I was just about to get a knife out. that big enough? That seems plenty. This is just hanging on by the last little bit. A little messy. Okay, well, there's our ground. So then we have VUSB on the other side. Let's make sure that's somewhere relatively out of the way and connect it to a wire that we can get access to easily. I mean, I guess if we wanted to be fancy, we could connect that to the power supply via a poly fuse. The part of me that, I mean, like, if I were just experimenting with this device at my lab 100% of the time, I'd probably just want it to accept an external power input for this. But for other use cases, you might want this to be more self-contained, so. I wonder how easy it is to get access to the 5-volt power from here. I just don't even want to go down that route. I would much rather have external power. So let's use another bit of this little Kynar wire, because why not? Let's tin this and tin that and stick them together. Oh, Tuco's about to sneak up on us. Oh, Tuco. Careful, buddy. Careful. This needs flux and less cat, maybe. Hey, Tuke. Let's maybe put some very tiny heat shrink around that. Maybe I don't have very tiny, but I have small. Now it'd be nice if this could help avoid that shield shorting out problem that I was worried about earlier. I think it can. Yeah, that's what I'm going for. Okay, so there's our USB with power and ground. Now it just needs some data, which we're pretty close to having. Let's attach the other end of this to something convenient, like maybe this pin. Oh, Tuco, you found a bolt. Good job, little guy. Where's the camera? Oh, it's way over there. Okay, attach the other end of this. I don't think we need to bother with insulation on this end. Tin that. Tin this. Stick them together. Way off screen. Oh, an interesting question from Jarrett. Randomly, when you clean flux with isopropyl, is it normal for it to leave a white haze? Sometimes. It depends on the flux. I really don't like flux where that's the case, so I've been trying to avoid it, but yeah, I've had flux where that's the case, and it's terrible. I end up having to go back with... I've used there's like flux removal spray. I think it was from like MG Chemicals or somebody like that. Yeah, and then you have to go back and use a combination of like that or other solvents, and I think Emily in chat is saying that acetone works too. Yeah, that just makes for not a fun situation. Okay, 5-volt in. What else do we need? So we have D- on top, D+ on bottom, which happens to match the order of our traces here. So, and the processor is to the left, so we want to join both of these to the traces and then cut them to the right of the joint. So I think I'm going to arrange both of these so that they can make contact in the right spot, and then do the PCB prep. So cutting the solder mask, well, shaving off the solder mask, and then actually cutting the trace. So right up against the board. This will be a bit temporary. Just need something thinner to get up underneath there. All right. Well, that's what I wanted. All right, so D minus, D minus, D minus, which goes to the inner trace. Oh, why do I have so little light here? That's better. All right, so I'm going to make a little land for this one. Right over here. Let's actually cut that from the other side so it's easier to not accidentally cut too much. Let's also use a less dirty X-Acto knife tip, maybe even a smaller knife. This one is smaller. Don't know if it has any other desirable qualities. I do just need a sharper knife blade for this part. Where's my Stacko knife blades? Stack of blades. Whoa, there's a spider. Like a big one. That's not a knife blade, but it's pretty cool. It's not like a tarantula, but it's fuzzy like one. Okay, it's possible I have to walk across the room to get a knife. That's fine. Oh, unless it's in here. Yeah, let's go get a fresh knife. Tuco likes spiders. I wouldn't want to try to see him get this spider with this mess here, though. This one's in better shape. Let's try that. that's the particular maneuver. So I'm just cutting the left trace right after where I plan to join it. And you can see it's completely gone. I'm not just like scoring it, I'm just removing a chunk of copper so it's no longer got any material to be connected with. Yeah. Okay, so let's do something similar for the next trace. Making a little shiny spot. Doesn't really matter if that's connected to the other trace, but it'd be nice to avoid that, just for a little bit improved signal integrity. Then that's the place where we make the cut. Ideally, this is a little V-shaped cut, so you come in from two different places and meet in the material, taking out a length of the track. And here I'm just trying to clear out some material. Very hard to see if that worked correctly. Let's try to get some more visibility. Looks right. So we can make ourselves another little spot over here for testing it with the multimeter, just to verify. Just taking off some solder mask where hopefully it won't get in the way of our soldering, but we can still use it to check continuity. Oh, interesting. That's a cool tip from US Water Rockets in chat. Well, a couple of tips. So WD-40 to remove the haze for when your flux turns white after cleaning it with isopropyl. Then to cut traces, make 2 scores a 0.5 millimeter apart and then touch the area between the scores with a soldering iron. It'll lift the piece right out. That's pretty cool. Yeah, I guess that weakens the adhesive enough that you can just take the trace out once it's hot. That seems really useful. I'll have to try that. Okay, looks like that's our trace cut there. Then here, yep, that should be a verification that the traces are cut. So I think we can position these to solder them now. Maybe using the tiny pliers. So right next to VCC we have deep minus, which is the interior trace. There's really not enough room to use those pliers, is there? have to hold this down to solder it, even though that isn't ideal. Let's just try to tin that track. Well, let's prepare the other one first. It'd be easier if we do these both at about the same time. I think my plan here is to do this soldering operation, and then let's power it on and test it. What we should see is we should still be able to connect to the serial port. We should see it not have a camera, which might cause it to complain, but we should still have a serial port. And we should be able to plug in other USB devices, like a USB storage device in here, and then see the device show up and maybe even mount the file system. So that's on the right track. Needs a little bit of soldering. Let's actually switch to the smaller soldering iron. Tiny soldering iron. Let's add some more flux. That's not a very good joint. So it's really hard to see the solder break. Did I solder to the right side of it? I think it was like right on top of the break, which is part of what was making this weird. Okay. That's also not great, but let's try soldering the other side before we get too fussed about that one being perfect. And where's our break again? Looks like it's just to the right of there. Let's get some more solder around that area. Some more flux, I think, and then just to be bent a little bit into the right position. I also need to tin the track under there a little better. Which needs less junk on the iron. And more flux. Oh, did that left one come off already? How did that happen? I'd like to be able to temporarily move these out of the way so I can tin these traces a little better. It's really hard to see what's going on in here. I think I may need to tilt the microscope. That just looks like a mess. Let's try some of this other flux. Debating using different tweezers too, but these are burly tweezers that I don't mind pushing on things with. I am not seeing where my brake went. Is it just to the left of there, maybe? Yeah, that brake is pretty obvious. Oh, there it is. Okay. I think that's pretty much what I wanted. Let's try to verify that that's correct. Let's give ourselves another little scraped off area here to look at. Should probably clean some of this flux off first, but let's do our test. Nope. Yeah, that's dead short. It's probably right there. So let's try to fix that. Oh, US Water Rockets is saying the first trace popped off. Is that true? And this one? I think they're both on. I think that cleared the short, but it's not connected anymore. It looks right. Let's try that again. Oh, this one. I see. Yeah, that one has a problem with shorting out also, it looks like. I don't want to have to put this under all that mechanical stress. Let's see if I can bend the lead a little bit better. I think that's hovering a little bit above both of the traces, and I can solder bridge just the one that I want. If they were shorting here, though, that would mean that my thing where I cut the trace is also not working right. So we'll have to take a closer look at that. That's not even gonna do it. Do a continuity test now, maybe? That short was concerning me. Probing through the goo is annoying. It does seem like they're shorted. Does not seem like this is connected though. So this is connected to that, which is expected. That's connected to that, which is not right. But then this trace on top does seem to be isolated from this. So, oh, is that? I think that's a solder blob. Okay. Inside the goo lies another short. Okay. Good old surface tension, keeping us on our toes. I think I got that clear. Maybe not. Oh wow, my laptop is going to restart all by itself. It's just like, you don't get a choice anymore. Alright. Okay, I think I have too much solder and too much flux and not stable work holding. The back side of this board being curved is super annoying. I think I might just tape it to a vise. There isn't even really a good way to hold this in the vise by itself, but that might be better than nothing. More light. Lots more light. That's a little better. Nope. Don't need that right now. Yeah, let's just solder braid that and start with less solder. Okay, now you can clearly see both traces and the break between them. It just seems like an improvement. Let's see if we can actually aim this where we want it. Kind of. These tools are enormous. Try to coerce this into doing what I want. Maybe with a clean iron. No, no bridge. I don't think that's going to make the leap all by itself unless I coerce it down. Okay. It's clear of the other trace. Okay. Let's see what we can do with this one. I think that's trying to lift the trace, which is not necessarily a problem, but sure. Definitely be easier to make a good mechanical joint with just running magnet wire. I was just a little concerned about signal integrity. This looks like the thing that I want. Let's clean this off and try plugging a serial terminal and a USB device into it. Where did I put my isopropanol? Also, where's the cat hanging out? Oh, there he is. He's back on the rack again. What's that, buddy? I'm trying to be really gentle with this and not scrub at it much, but still soak up some of the huge amount of flux residue. This might do for just a quick power on test. Oh, let's also make sure that these are successfully cut, that we don't have lingering connections to the other chip on this board. Back in continuity mode. It's not an amazingly conclusive test, but I'm not seeing anything with those two traces. Okay. So, for serial, I'll be using one of those blue prolific dongles, I think. This one. So ground. I think we'll want that order. This is me trying to remember which one's TX and RX based on how the connector was plugged in before. Okay, and then for power, we want the same 5 volt. I'm also going to attach a second 5 volts to the little fly wire we've just put in. And this will be for powering the USB device that we plug in here. You don't have to use a separate supply. I'm just using one so that we can keep an eye on the current separately since I have a dual output supply handy. So ground could be pretty much any of these. Just trying to put these somewhere where they'll be out of the way for the next couple of experiments. This might be a fool's errand. We'll see. That'll do. Set that to 5 volts. Current limit at like half an amp. Okay, let's get a serial terminal and see if we can watch this thing boot. Let me turn on the DSLR grabber. So the other end of this goes on the floor. I think I need an extension cord. The USB hub is farther away than usual because my lab is disorganized. Low USB cables. USB cables in the shop. It's hard to believe I might ever need more USB cables. Okay. Hopefully the drivers are still smiling on us and we see the serial port we expect to see. Kind of. Cool. Okay, I think... Is that the right baud rate? I think this is already set up the way we want it. Let's try plugging this in. There's our boot up. did I just... Oh, there it goes. Why is the OV780 showing up as ready? I'm not expecting to see that device on the bus. I wonder if this is actually it waiting for it to be ready instead of it being ready. I think this is what we want. UVC stream not exist seems like a good sign. This might just not have much error handling. I doubt, so we don't have LSUSB, which is normally how we'd find out what devices are there, but we have proc bus USB devices. HCI controller, OHCI controller, and that's it. So no devices. These are just the standard kind of high speed and full/low speed controllers that you'd find. So, and we don't have dmessage. Is there... I forgot if there's a way to get dmessage using sys or procfs. Let's check that really quick. No, that's not what we want. I don't know if there would be anything in proc or sysfs, because normally I don't think the kernel actually stores those messages. I just thought there was a buffer that dmessage reads, like even if the syslog daemon is broken. Oh, is that it? Proc kmessage? That doesn't quite seem like what I want. Oh, maybe it is. Those are all queued messages that I guess would be logged if there was a log daemon running. I was just trying to find out where we would get kernel logs, because that would be one of the easier ways to see if a USB device is detected and what it's detected as. But besides that, we can also just cat procbus USB devices. So let's try actually plugging something in now. So we'll turn on the other power supply, 5 volts, currently no current drawn. So this should be a live USB port now. I'm just going to plug in a flash stick. Don't think there's anything important on there. So drawing 60 milliamps. I don't know why we're seeing a new driver registered for USB serial. But now if I cat procbus USB devices, we see USB disk. So I think we've got it. This is our USB port. Speed 480 means it's in high speed mode. Oh yeah, looking at catching up on chat a little bit. So sys kmessage or proc kmessage? Yeah, so we were just looking at proc kmessage. Let's see if there's a sys kmessage. Maybe it's named something else in sysfs. Yeah, let's just see if there's anything new in proc kmessage. So I don't know why it's registering a USB serial adapter. That's pretty weird. I'm wondering if this device momentarily detected as something different. Anyway, it eventually detected this as a disk, I guess. I don't know if this would have a USB storage driver, though. So, you know, if we look for dev SDA, you know, there aren't any SCSI device nodes like you'd find for a disk. which could just mean the device nodes don't exist, but it could also be that they didn't include USB storage support in the kernel. I think actually Profibus USB devices would tell us. Oh, interesting. For some reason, the USB serial driver bound to this disk. So it might be that this. That's really weird. I don't know why this would be happening, because it's clearly reporting a storage device class. Maybe there are some circumstances when this can happen if the kernel doesn't have a storage driver, but this is pretty weird. But this does mean that we probably have a USB serial driver, so if we wanted to give this thing an additional serial port, we could plug one in. I don't know if there's an easy way for us to see which USB drivers might have been compiled into the kernel. We probably don't have proc kconfig, which would actually tell us what the kernel configuration is. That's not useful. Oh man, the camera driver is really cranky. It really wants there to be a camera. Oh. Is it just going to spam us with those every so often? Okay, well, we might have a limited number of driver options. It could be even a little bit annoying to figure out which drivers are compiled in, other than with some hints like what we're seeing here. But we can still move on and attach the other end of this USB connector and do our man-in-the-middle thing where we're looking at the USB traffic with an analyzer. So, I think this was a good milestone. We've got what we want so far, but let's go back to soldering. I'm not going to bother shutting this down. That was the device disconnecting when I powered it off. And then I immediately afterwards powered off the camera. Oh, so Sodium is saying they've always seen the kernel config at proc/config. I thought I checked there. I think that's an optional feature that would usually not be enabled on embedded systems. But let's check really quick. I forget whether I actually looked there. Let's also try booting with that storage attached, even though I doubt that would be useful. I'm also curious if they would have support for like keyboards, but I don't know why they would. I mean, they have no reason to include kernel support for any USB drivers other than this particular camera, which might even be a user space driver. Click, click, click. OV780 firmware ready. So we should be able to see that whole initialization process once we have the analyzer looking at this. See it loading firmware and all that. Got a command line yet? Almost. It's still all like, wait, dev video 0 ready. And I'm like, it won't be. I don't think we have any config stuff. Yeah. File systems. They were nice enough to install USBFS, which means we can use user space USB tools. So if we compiled LSUSB for this architecture, we could use it without having to, recompile the kernel. If we compile our own, like user space, like if, for example, we could like statically link or just bring in all the libraries we needed for like Python with libUSB, and we had RAM for that, then it would be a nice way to just poke at USB devices. But let's try plugging in a USB serial device while we have this thing booted. That looked like, now I'm trying to remember, do I have anything that uses just plain old USB CDC serial? Well, I know the Blackmagic probe does, and I have that right here. We could try plugging that in. I'm sure I have other devices with CDC serial, but this was handy. And then a cable. This takes micro. This one will also be a little bit different because I assume this is not high-speed USB. I assume this would be full speed, but for sure correct me if I'm wrong there. This I'm mostly just trying to see if it has a driver for the serial ports that we'll see in here. So I would expect to see, if I do cat /proc/k message. So this is just draining the kernel's buffer. But I expect if I did that again that I would see some information about this device once I plug it in. Well, we might see some info about unplugging this first, so let's do that. Being so gentle with this. We've also got messages on the console. Maybe those are going to be the same messages. Okay. Maybe they just have console spam logging, which is cool. And new full-speed device. Maybe this does not work with their USB serial driver. HCI host. Here is the Blackmagic probe. 12 megabits, so it's full speed USB. I would expect this to load with the serial driver. Maybe they intentionally did something weird here where they hacked the USB serial driver to load with the storage device class. That would be really, really strange though. Because these are, at least some of these are normal serial driver or endpoints. Okay, well, that was fun. Let's unplug that carefully. Okay, well, let's do the rest of our soldering and see if we can just give it its camera back. Oh, or another last minute suggestion from Sodium to look at lib modules to see if there are any information about the kernel built in. Yeah, I don't even know if we'll have a lib modules, but let's take a look. I mean, this is a really minimal system. I guess we have it. Like, this entire thing is living out of init.rd. Ooh, USB. Well, maybe that's all we got in their modules. Well, maybe this has to do with the module auto-loading being weird. Let me try manually loading. Thanks. Okay, well, I'm not going to go too much deeper into that. I think I just want to put the other connector on there and we can watch this thing talking to its own camera. So this one's pretty minimal. It might not have a lot that you can do without loading additional drivers, but on other devices, this might have some interesting ways in. Let's turn those off. Alright, so we can take this stuff off for now. That's the USB power. This was the main camera power. And looks like over here is the area where we wanted to add a new connector. So this just loops around from here. And just like over here, D- should be on the inside. So here we have ground, D+, D-, VCC. So let's get a pin out handy. I'm going to use this type B connector this time. VCC this time I can just leave off entirely. But the other pins are going to be important. checking the requisite pinout images. I think this one's right. I was just cross-checking it against some of these other ones. Sometimes you find incorrect pinouts when you just Google for them instead of looking at the actual spec. And sometimes they just aren't labeled very well. So we want the USB-B. So 1 be down here, VCC. Okay, I believe this pinout. So D- goes on the inner track. I'm just going to cut the VCC lead short on here since we don't need it. And that'll help me remember which one's which. So now I have D- and D+, which happens that if I put it on the board like this, then the one that's closer to the inside of the board will be on the inner track, D-, so that lines up nicely. And then ground, I'll need to put that somewhere sensible. So, and again, this is the side that goes to the camera chip. So that's the device we're trying to connect. We want to place this somewhere along here and then cut the trace so that we don't end up with a stub. So I think I can actually basically just put this right on top of there. We'll have to solder from the side again, but we should end up with a nice connection, I think. Something like that. Let's try making this a little bit easier. I'm dislodging the pins from the back of the USB Type-B socket just a little bit so we can get easier access to them. So I bent these so that D+ and D- come pretty close to each other, and then there's ground hanging out kind of far away. So those two, and I'm just going to take VCC entirely out because I don't want it shorting anything. And then I can bend this ground back a little bit so it'll be easier to get to. And then flatten the tab so that I can solder this directly on the board. So, got these little wings all flattened. There we go. So then this is mechanical mounting, which is probably also going to be ground. This pin that's sticking out by itself is ground, and then these two are the differential pair that would go to the traces right next door to each other. Let's bend this ground a little differently. Not put it directly into my thumb. Actually, I just bent off part of the ground that I wanted. Oops. Okay, well that will require a tiny wire then. You can see I broke off that ground pin. I didn't really intend to do that, but it's fine. So I'm going to start by scratching off some spot on the ground plane to attach this thing to mechanically. So what do we have over here? That looks like power or something. I also solder this by the edges, which happen to be right on a nice ground plane that would be sturdy. Well, let's do what we can over here. Quite a texture on the silkscreen on this board. I'm kind of adjusting the angle that I hit the board with to change how much material I take off at once. Being maybe a little too conservative with it at times, but... You can see it kind of flakes off where the epoxy covers the copper. Okay. Where's the other spot I wanted? That looks pretty clear. There's some ground plane vias in there, but nothing that'll be annoying to hit. Grab all the junk off the front of my knife, and then I took the whole blade out. copper is pretty soft, and it's easy to start going too fast when the copper is exposed. All right, let's tin those. Using not the tiny soldering iron. That'll be enough. You can see this one's already pretty hot from the soldering I was just doing on the other side. Alright, let's put the connector on. Trying to carefully line it up as we do so. Just tacking that down so I can check the alignment. That looks pretty good. That little wing is going to start touching some of the circuitry up there, so I'm actually just going to solder it, hovering a little bit, and then break off the little wing. Bend that down at all? I press it down. That might do it. That feels pretty solid. Try to break it off, or do I bend it down so I can solder it? I bend it down, but I try not to break this capacitor over here while I'm doing so. This'll be a huge mess. Is that still connected? Yeah, okay, let's solder the other side a little better now. Oh, sorry if anybody's asking questions in the YouTube chat and I'm missing you. The machine that I'm usually viewing that on decided to update and reboot during the stream. Oh, can I get that back, I wonder? Maybe on its way. Okay, so those grounds. Now we need to fix our missing ground here. We can use just using a little fragment of wire. I'll tin my fragment of wire, and then we will stick it on there, as is our tradition. A little ugly and a little out of focus, but I think that'll do. Oh, that was Tuco repositioning himself around the computers. Stick that down there. Now we need to nudge these out of the way just a little bit so we can scrape the solder mask and cut the traces. More of the heat is going into the wire than I wanted. I really need to heat up the ground plane, and that's just melting the solder on that upper joint. I'm having a hard time getting the solder into the position. All of this other stuff in the way. Come on, solder. There we go. That's a big mess. Let's try to clean up that connection above here just a tiny bit. If this was a stereo microscope, it would be clearer just how much stuff there is in the way here. Alright. Isn't pretty, but it'll do. Okay. I think we need more light there. Okay, so the chip we're connecting to is to the right of this. So I think what I want to do is scoot those connections left, or scoot them right just a tiny bit. Then to the left of them, make the cut that we need to make. And I'm going to have to be careful not to have these short out on the ground plane. Maybe we'll try that heat-assisted trace lifting technique. I don't know if that's quite scored enough. Maybe not. I don't think I quite did that right. That is a little bit of the trace lifting up. There we go. I think that is sufficiently trace cut. Let's try to test that a little bit before we solder or goop it up with a bunch of flux. Yeah, Okay. That looks fine. Let's add a little flux, do a little soldering, and hopefully we can get the USB reconnected so that we can inspect what's going on. Little flux booger. And switch back to the tiny soldering iron. Maybe this is a good time to try to reshape that so it isn't shorting. Alternatively, I could try to slip some Kapton tape underneath it. Maybe that's what I do. I don't really want to lose the bending that I've got it positioned just right. I think Kapton tape will be a sufficient amount of protection. Some really little Kapton tape at the end of it fell off my dispenser apparently. Here it is. Gooey. I could cut this, but it's also satisfying to bunch it up so that I don't have to cut it. There's so much crud on my iron. I'll need the tweezers to hold that down while it cools. That's not working. could use a little more solder, but it's probably fine. Okay, let's see if that works out. Let's do a multimeter test, and then try actually connecting that to some USB thing, probably an analyzer. Let's give ourselves a test point over here. There's the stage where you're scraping, and it looks like it might be copper, but it really isn't. It's just kind of orange. And then once it gets actually shiny, then you've got the copper. Great. That's what we were after. Nothing like Kapton tape soaking wet with isopropyl alcohol. Oh, thanks for the notification. I don't know if I'm going to end up using the DSLR footage from this run, but it's always good to have it handy. Okay, so we have these two USB ports. Let's try connecting some cables. I'm going to try to find two pretty short type A to type B cables. We could just go ahead and connect them directly, but I figure I might as well connect the analyzer. This whole setup is a little fragile, so just not unplugging and plugging in too unnecessarily seems good. Well, here's... I guess we have some cables. Might as well use these. So I'll plug this one into the type B up here. These are both going to the Beagle USB analyzer over here. Let's get that in frame. So yeah, lots of things we could do with that, but right now this should be pretty much straight through. Then we'll want our serial port back. Where did that go? That is on the floor. I'm forgetting what order these go in, so this might be backwards, but it's no big deal. The serial, not the USB. And the USB being backwards wouldn't be that big of a deal either, but that's 480 megabits instead of 56 kilobits. Oh yeah, I mean, lots of people suggest that I should switch cameras or fix bugs in Magic Lantern until it works for me. It's just a question of what I have energy for. I could be making electronics videos, or I could be fixing bugs in Magic Lantern. So, like, I'd kind of rather not put that much more energy into this camera. Especially when, like, I could just keep using this camera and then eventually upgrade to a 4K camera or something. If you'd like to fix this bug, then that'd be great, and then maybe I'll use Magic Lantern, but like, that's the kind of bug that's tough to fix, like the kind of bug where occasionally it just nukes someone's SD card. Because if that happens like once, that's enough to make me not want to use your software. And having, like, kind of stepping in and trying to fix a bug like that for someone else doesn't really work unless you have the follow through to make sure that it actually doesn't happen, like, over a long period of time. So that's a difficult kind of thing to just do. It's not like a problem that you can just kind of like barge in and solve usually. So I think we're ready to power this thing up. So let's go back to the serial terminal and then turn on our 5 volts. Do we have console? Yes, cool. Okay, let's open our USB analyzer. So that would be the data center software from Total Phase. And I'm not going to start the capture quite yet. I just want to poke around and see if the camera's working, but then we'll reboot it and start a capture. We could also even potentially like see the camera output from this thing. That might require plugging it into my network again. Which is another long wire somewhere. This is different, H.264 frame size. That seems like the camera's happy. If config is not happy because it's not on my network, but that's fine. Yeah, it looks like the camera's fine. Let's just take a look at Profibus USB devices. That looks like the camera device again. XXX Technologies, but it's the UVC video driver here. So that's interesting. It is a UVC, so this is the standard USB video class. So we have the kernel UVC driver giving us like dev video 0, but we also have this OV780 user space process that is talking to it somehow. So that could be USB, it could be vendor-specific interfaces in UVC video. That might be worth looking into. Okay, let's reboot this thing with the USB analyzer running. Power off, power on. And now we're just waiting for it to get to the part where it's actually doing USB traffic. Still getting the kernel started. Am I not recording properly? Because I would have expected it to talk to USB by now. That's interesting. Maybe let's restart the software. I would also kind of expect to see that, like, I think if we actually cap Profibus USB devices, that would generate USB transfers. I don't think the kernel caches the strings in here. But we are currently not getting anything, which is not good. Let's just check the situation, maybe using a completely different host and device. Would that be useful? I don't know why we're not seeing anything. Unless there's like a problem with... Oh. Right. I don't need to power anything, but the Beagle actually checks to see if the USB is high. Maybe I can override that. Oh. I think it's easier just to supply VUSB. Let's try that. So for that, we'll need this little power supply again. Shouldn't expect it to draw any current really, but... And that would explain why the camera seems fine, but the analyzer is complaining. Okay, let's turn on that 5 volts. No current draw. Oh, look at that. Look at all that chatty camera traffic. Okay, cool. Let's do a fresh boot. So power off. Let's clear this. Start a new trace and power on. So I wouldn't expect to see this start until after Linux is booted, but then it probably starts pretty soon. Uncompressing. And uncompressing the init.rd. USB reset, and now it's talking. UVC video driver is doing its thing. It looks like this is decoding a lot of that, actually. And then UVC stream starting up. So that's probably it actually running a daemon that's grabbing frames and sending them out the network. So we can filter this some more too. We don't need any of these. So this is just it polling for input data, which we can kind of ignore. Filter. I think we can use the stuff over here to filter out what we want. So this is showing us USB 2 packets. I think we want to try... So all of this stuff is... These are not actually data transfers, these are attempts to transfer data, but then we do occasionally see actual data transfers, so I was just trying to filter this a little bit. Maybe what we want is on this pane. Oh, there we go. Incoming records collapsed. I forgot what button it was on this UI. Okay, So these are in on which endpoint? Endpoint 4. So this could be a lot of things. This is most likely some kind of flow control data for the video endpoints. There's going to be a combination of video, audio, firmware loading, parameters. If we go up to the top, we should start to see, yeah, this is like the video device configuration. So first, here's the regular USB stuff, get configuration descriptor. It's just figuring out what driver to load, getting strings. This is the stuff that you see in LSUSB or in Profibus USB devices. XXX technologies. And then it starts setting up actual UVC specific stuff. So stream interface num, this stuff, these are UVC commands. Setting up volume controls over and over again. Set. So yeah, a lot of parameter type stuff here. I'm curious if we can see the firmware loading. And it wouldn't be any of this stuff. We can over here in the sorting here, we can find packets per endpoint. So if we go to data 0 packets, we can, so the data packets alternate between 0 and 1 usually, or they added a third for super speed. But if you just look for data 0 packets, that'll show you the first, like that'll be like the even numbered packets in the stream, and data 1 will be the odd numbered packets. And then you can see them coming in by endpoint. So EP3 in and 4 in are polling pretty frequently. EP0 control had a bunch of stuff during initialization. I don't know if this would be video data. So this is, looks like 4 and 5 are these little packets coming in. So if we had this filter, oh geez, the filters here are slow. So this is just looking at endpoint 4. These seem to be, oh interesting, up here there is a bunch of data coming in after that little 3-byte header, but it looks like it's normally idle. Not sure what this would be for. Okay, here's yet another view that you have. This is showing all the packets that are coming in broken down by kind of what part of the USB device is handling them. So USB 2, we have some, so unknown device and unconfigured device would have been from earlier stages in the boot process before the device has been assigned an address. But then here, USB camera, I think Aoni is part of the vendor string, or maybe part of the vendor ID number. So then you can find endpoint 0 packets. These would be how it was configured. Then here's the stuff that's actually still coming in. So these are video streaming packets. I think this would just be indicating that the video stream is off, because I don't think the video stream would be on right now. But that's enough data that maybe this is actually on. Let's take a look at this. This is the isochronous stream where you would actually expect to see video data. Yeah, so this might actually be video. It might just be polling much more frequently than the frames are actually coming in. We could definitely figure out exactly what this is by reading through the USB video class specifications. Oh, I guess we ran out of memory. Thanks, 4 GB limit. So it looks like we've got a header per packet. I'm almost expecting to see like a JPEG JFIF header in here, but I don't know if I'm quite that lucky. There's maybe one other thing we might want to try with the setup, which is just connecting the camera to a to a computer, like to this Mac or to a Linux VM, and then seeing how we can poke around with it. Because there's a lot to go through here, but this is all the traffic between the system on chip and the USB device. You could mess with it pretty much arbitrarily. So let's see, for this step I'm going to unplug the camera from the USB analyzer. So you can see it's pretty unhappy with that. And then I'm going to oh, it's shutting down something. Oh, shutting down just the video process. Okay, this, I think I need a slightly longer cable for this. Alright, a little extension cord. And I assume macOS probably will not have drivers for this, but maybe if it's UVC it'll work. I suspect Linux will know what to do with it, even if it doesn't have the OV780 control program that we're seeing here. Alright, this will ignore the VUSB, it'll just have D+ and D- connected. Okay, so I just plugged it into the Mac. Let's tape this to the desk. Okay, let's see if we can see it in IO Registry Explorer. That looks like it. USB camera Aoni from XXXX Technologies. I wonder if we can actually just see it in Photo Booth. Do I have Photo Booth installed? Yeah, I don't know if we're gonna get that lucky. Maybe VLC. Can it do 640 by 480? That seems the video. Is it just pointed at a dark surface? Oh, look at that. Let's maybe free this slightly. I don't need this power supply connected anymore. Or this clip. Or this one. Hi there. Got some Kapton tape in the way. So, can this do any higher res modes, I wonder? This thing is not happy. It's still working. I'm very gentle with the wiring here because it's pretty delicate. I'm curious if there's anything in here that tells us about the modes that it's supporting. I'm sure there's some utility. I mean, especially on Linux, I'm sure there's like a UVC utility we could be using for this. Can we do 1080p? I doubt it, but... Whoa, is that 1080p? I think it's scaled 640 by 480 to 1080p. That is definitely the wrong aspect ratio. Maybe, do I have a Linux VM handy? Because we might see more in a Linux VM. Oh, Piotr in chat is pointing out that the photo booth was working. We just couldn't see it because it was facing the table. Oh, maybe I had this... Yeah, I don't know. Well, it's on the right camera. Maybe that was before I opened it in VLC. Maybe I need to quit VLC first. Oh, now it says no camera available. Huh. Is that a fluke or did I break it? I might have just temporarily lost the device, actually. Let's try replugging it. Unplug and... Come on. You know you want to come back, little device. Why are you not coming back? Did it lose firmware or something? Let's take a look at the serial port here. Let's try letting this reinitialize the camera, maybe? Let's unplug this from the Mac and plug it back into the camera and then reboot the camera, maybe. Well, there it is plugged in. Device not accepting address. I think I crashed the camera. Let's try power cycling this. So one question to answer would be, does the camera work on its own, or does it need a driver download, or like a firmware download before it will show up as a UVC device? So maybe that would be something we can answer. Like we could try that by just powering it off, powering it on, getting it stuck in the bootloader, and then trying to talk to the camera externally. So right now I've got a loopback USB plug, so it should have control over its own camera. And it looks like 640 by 480 might be the highest mode it supports. So, alright. Well, it should be fine talking to the camera, so I think we can steal its camera connection now and plug it back into the Mac. Very carefully steal this wire. And plug it in here. There we go, USB camera, AONI, and it lost my mouse, and then it lost the AONI again, and then it came back. This might be a problem with my USB hub situation over here. Oh, there's my mouse back. Okay, let's see if we can run Photo Booth. Did I lose my keyboard also? Come on, keyboard. Keyboard is flashing like it doesn't want to stay connected. Power cycling the hub might have fixed it. Maybe I crashed my USB hub. Maybe that was the issue. It is a USB 3 hub, so I'm sure it runs some serious firmware. Let's try the photo booth again, just so we can verify how crazy we are, respectively. So it's running now. We're seeing the camera up there. Oh, yes. Okay, great. So it probably did work the first time. We probably just crashed it afterwards. Great. So there we are, talking to the camera externally over USB. The back side of the case is what actually has the tripod mount, so it's hard to kind of hold this easily. But I think that's it. I think that's about all we're doing with the camera now. 640 by 480 video. Partying like it's 1998. Hey Tuco. Whoa. Tuco, are you ready for some playtime? Well, I think I'm about out of ideas for this stream unless anybody else has some suggestions or some questions they'd like me to answer about this. Oh, that was the IR filter clicking. Nice. Did it just turn off the IR filter? Click. Interesting. Hey, Tuco. Man, this is an interesting little device, but a 640 by 480 camera is just not that appealing for most things. So it certainly has some hacking value, but I'm not really quite sure what to do with it otherwise. But we got the USB. We got the USB on the system on chip and on the camera, and we can get in between them. Oh, right. Robert is reminding me to try seeing if it needs firmware. Good call. Let's try that. I described that whole test and then completely forgot to execute it. So here's the camera operating. So we want to probably disconnect this from the Mac first. And then let's go back to the terminal, power this off, give it a few seconds just to make sure the firmware is totally gone. Pet the cat. Move the cat camera. Alright, powered on. Get it stuck in the bootloader. Alright, cool. So now we can plug this back into the Mac. Am I going to need to reset something first? Oh, it's also possible that the camera is not actually turned on. I might have to let it boot for it to turn on the camera. Let's just reset my USB hub just to make sure that's not the problem. Wildmania is asking, is it just me or are my video and audio out of sync? I suspect my video and audio are out of sync a little bit. I haven't had time to fine tune it since porting over my setup, but it shouldn't be out of sync by more than like 50 milliseconds or so, I would expect. Okay, so here's my hub. I'm still not getting a camera. Let me try just unplugging that and plugging it back in. Okay, still no camera. Well, so I have that connected to the Mac still. Let's boot the system normally, maybe. Can I just reboot this? Well, let's just power cycle it. So I'm expecting to see a new USB device up over here at some point during startup. And this is assuming the camera needs to, or this D-Link board needs to turn on the camera chip, but it wouldn't actually be connected to it in order to load firmware. So the hypothesis would be that there's like a GPIO controlled power switch somewhere on the board that this is hitting. There we go. So I think it did have to turn on power somehow, which happened sometime around here. So maybe this OV780 binary that they have does some power control as well. So we have this device. It would not have firmware if that's a thing. So are we seeing a class here? Don't remember off the top of my head what device class that is. But let's see if photo booth works. This is not seeing a camera. What is this? Device class EF. Let's see what the device class is supposed to be for UVC. I just wanted to know the number. Well, I'm going to assume that this is something that isn't the video class, probably. Let's try maybe letting this thing load firmware and taking note of what the class is and if it's different. So here the device is EF. I think that on a real video class device that this would have classes set per interface. You know, I really don't like IO Registry Explorer. I'm going to go back to USB Prober. I like USB Prober. Because this actually gives me descriptors decoded and not just the information the drivers use to load. So, miscellaneous class, huh? Is this maybe... No, actually, here's the camera. Here's audio. Maybe photo booth is just not seeing it for unrelated reasons. Let's see if VLC sees it. Let's restart VLC just to make sure that wasn't stale. Robert's asking is it possible there's an auxiliary I2C or SPI or whatever kind of low-speed bus to bootstrap the camera? It is certainly possible. I would expect them not to do that just for simplicity, since this is a camera chip that's designed for standalone USB cameras, but it's certainly possible. Yeah, that must have been stale. Let's try unplugging the USB and plugging it back in. It might also just be that there's something that happens over USB that's non-standard that we need in order to initialize the camera. So it was here, and then I unplugged it and plugged it back in, and it didn't stay. I'm wondering what that might have been about. I just rebooted the hub, but it still is not coming back. That's interesting. I wonder if a USB reset causes the camera to power itself off until something comes in externally. That is odd. Let me try power cycling the camera and see if I can get this to come back. So this is still waiting for the kernel to boot. This should show us the camera come back if it's going to. I know the card is full, I just don't care. Fine. Yeah, interesting. So it is coming up during boot. Yeah, it's definitely possible there's some kind of auxiliary bootstrap. I just don't know why they would design it that way. It seems more likely that the camera has some kind of power on-off control that would normally be controlled by some external circuit in a standalone camera, and that here they've routed it to a GPIO maybe. But that's still a little bit weird. Like, is this OV780 thing just a standalone binary? Oh, there's a couple of different ones too. Yeah, so we could do that. Just capture the binary and take a look at it. I don't know if I quite care that much. Like, it would be kind of nice. Maybe we can just take a look at where that would be used. Do we have grep even? I mean, it does definitely seem like this is sending firmware. I mean, where was it? There's a firmware binary just hanging out in /bin, if I remember right. Maybe it was somewhere else. Well, it would probably be a little less annoying to just unpack this firmware image elsewhere and take a look at the root file system. Maybe we should just do that. Do I not have bin walk on here? Ben is asking if the firmware was in /temp. I don't think it was /temp. I remember seeing it somewhere. sts.dat. I assume that's a status buffer in binary. No, I thought it was in like bin or user or something like that. Andy. Hi, Andy. We've got some header files, courtesy of Andy. Probably nothing that isn't just in the public Linux distro. Okay, binwalk. Let's see what binwalk thinks about this binary. Yeah, let's extract this. So we want, I think we want to recursively extract stuff. Yeah. So this is just unpacking everything it knows how to find in the firmware, which should give us a slightly easier way to deal with these files than actually slurping them off the camera. Huh. In this mode, it's actually going to try to extract stuff from all of these other files, which is maybe a little excessive. But what did it find here? H.264 plugin.dmg. Neighborly text. So this is going to be the browser plugin that they distribute to Mac clients. Not quite sure what that would be. Alright, let's inspect the spoils of our extraction. That looks like it's kind of a separate file system for the website. Or this is just the root FS. 3B000, I guess, is mostly what we're interested in. So that was the original LZMA, and then the, what is this? These CPIO files. Is this the root directory of their file system? No, I think I just extracted everything into the same directory. Yeah, I don't think those were the extraction options I actually wanted. Let's try that again, maybe without the Matryoshka option, because I think that's maybe a little more crazy than I want. Let's try just E. LZMA. Okay, so that didn't extract everything we wanted. That got us a couple of different firmware chunks. So it found 2 of these U images. I don't think this is right. I think this is just a false match. I think this is their SPI flash image header. I think this is actually the kernel image, because that's where we would expect to find it. Is that we did look at the MTD layout earlier, and we saw that at this address, 50,000 hex, that's where we would expect to find the kernel, and then right after that is the initRD. So both the kernel and the initRD are LZMA compressed, so I think this is the chunk we care about. The rest of this might be interesting for kind of runtime data, but this is going to be the data we care about for the kind of firmware proper. So that's what we'll see inside this 50040 directory. Oh, that isn't a directory, sorry. So I think we can just so I think this gave us a header so we can un-7-zip this if I have 7-zip installed. Maybe that's not right. Maybe this is actually just raw LZMA data. So we extracted that. It's another... is that... I think we actually need to tell binwalk to extract that. I think that's the problem. So we were using E, which extracted all the chunks but didn't actually like un-LZMA the archives. Yeah, maybe this was right. I just don't know why we're getting so much spurious data and why the files were not ending up in the right directory structure. What actually is this file that it's giving us? So if we binwalk on the firmware, what actually is this 10 megabyte chunk? So this is, starts off with some zeros. This was from 50040 hex. I assume this is LZMA data. What is this? I mean, that looks like actual compressed. Oh, okay, this is the uncompressed data. So it did uncompress it, and now I've got this, which is probably a file system image. I don't know why binwalk... I guess binwalk was just carving files out of this, but it didn't actually extract this properly. Is that what's going on? I don't think file would know about that. So this I would expect to be, yeah, this is the disk image and the kernel. Well, so this is going to be the kernel, and does it include, like, does the kernel... I guess I'm not quite sure whether they would have compressed the initRD, compressed the kernel, and concatenated the two, or whether they compressed the initRD again, which seems a little bit weird. But maybe that's what's going on. I think this is the chunk we're actually interested in, which is after the kernel. Okay, we've got these two pieces. So this thing at 319,440, what was that? Okay, that was just the header for this, for the Linux kernel itself, I think. But then this chunk was actually the file system, I think. So what's inside 3B000? Oh, that isn't extracted yet. Ah, this is the CPIO archive. See, like, I think the Matryoshka option was mostly what we wanted. I just don't know why we stopped getting paths for most of the files. Maybe I missed an option that would save them with full paths. So this looks like it's just a CPIO archive, maybe? Yeah, let's try un-CPIOing this. Do I have that? So... how do you extract one of these? -I? I guess that's... so then that would be... oh, did it already extract these? Yeah, so it extracted them, just not with full paths. So this isn't really what I wanted. Great, yeah, I don't want that. That's not at all what I want. Thanks, CPIO. Can you chop off the leading slash, please? This is not a good archive tool. Oh, let's see if the internet knows. Okay, no absolute file names. That's what I want. Ah, what a terrible default for an archive tool. Really? Is that just the Mac version being special? Oh, maybe I shouldn't be doing this in Mac OS. Is there a better version of CPIO I could install? Oh, man. It's like tempting to just do this inside a ch root, but Mac OS. So maybe we switch to a Linux VM. So can we move that in there? That's not working. Oh, so frustrating trying to get files into and out of the VM when the drag and drop isn't working. Is that right? 38? Yeah. Okay. Let's try this bin walk experiment inside the VM instead. Yeah, I wonder if maybe binwalk was giving me less optimal results in macOS because of the version of CPIO installed. I don't know if it uses the system version or its own. Looks like it. They try to call it with no absolute file names. So I bet they have a hack for Mac OS that just gives you less good results. Let's see what's actually going on in here. I don't know why that just doesn't completely fail on Mac. Then walk. Okay, let's try the same thing we did before, but Matryoshka and extract, and we'll see if we get better results with the less broken binwalk, or less broken CPIO rather. We could also use the firmware images that we extracted directly. Let's use the one we downloaded. It's finding all the CPIO goodies. Trailer at the very end. I think that's a CPIO thing. Okay. TCS whatever extracted. 50040. 3B0000. CPO root. Yay, now we have paths. That was totally just macOS's binwalk being not so great. Well, now we have our file system. Let's find the firmware. I think it actually had a pretty obvious name. OV780 SPI firmware.bin. OV780 USB firmware.bin. So I guess they have options. I wonder what the differences are between these two. So maybe, man, if that's the same chip and you can just configure it to talk over USB or SPI, that would actually be a nice oracle for trying to reverse engineer the firmware, having these two different versions. Oh, and these are little, 89K, and the same size, which is nice. OVTF, the DWEB SDK. It looks 32-bit. Are these ARM instructions? I don't know. Or maybe it's 16-bit. See these? Are those 16-bit operations? This is not very big. Oh, and we have some strings at the end. Sensor proc. All OVF. Webcam SDK underscore USB only. Video die restart. So they've got an SDK somewhere that lets you write software for the webcam itself, of course. It's pretty small. It's probably just a little microcontroller, either like an 8-bit or 32-bit thing, handling, kind of configuring USB. Here's the USB descriptor that they didn't bother setting. The one that's like XX technologies. I wonder if we can edit this firmware and if it'll just install whatever we add. So then we have that OV780 tool, which I think was in bin. Yeah, that's the one that's 49K. I wonder if these other two are just wrappers around OV780. Not necessarily. Huh. UC libc. Yeah. So this looks like it can send SPI commands. It has GPIO stuff. There might still be an SPI control channel that it uses to send the firmware, and then it just talks over USB. I'm just not really sure why they would implement it that way. Maybe in a standalone webcam, there would be a standalone like EEPROM with the firmware on it, but here, to save cost, you can just send it in software from another processor. This definitely seems to be concerned with... Oh, there's a reference to those files in temp that we were talking about earlier. This looks like it might be pretty straightforward to reverse engineer. I wonder what the IOs look like. Do we see anything like devmem or like an SPI related device perhaps in the strings? This does explain the command line options at least, so there's probably a dash help. Well, that was fun. Look at the usage flags. Yeah. Yeah, let's try maybe... Oh, I guess Piotr said what I was saying before about it normally loading firmware off of an EEPROM, but then having an option for emulating that process. Yeah, I missed that earlier, but that was a really good guess. I think that's probably what's going on based on what we're seeing so far. Yeah, maybe let's try running that OV780 tool and just see what the parameters are like. So the camera is still connected to the Mac. This might also tell us, might also tell us what it can do without the USB connection, if anything. All right, so here's USB prober again with our camera down here in the not being especially camera-like kind of mode. And OV780. SPI command delays. SD card command. So maybe there's a model where there's an SD card connected directly to the OV780 chip. I want to find instances where the boot scripts are calling this command, because I want to see what it usually does to load the firmware. That would be easy to do over here in the Linux VM. Just grab what we've got for OV780. This is saying it's reloading reloading OV780 firmware. That's video.sh. I saw that name in the boot logs. Video.sh. So there's a UVC stream service it runs, a PCM command thing, which might be PCM audio. H.264 compression daemon. That's the only place where it calls that OV780 tool. So what are -R and -I for? -R is a reset time, -I, so these are just delays. Well, let's see what happens if we just issue this command. So So I don't know if you caught that, but the device just reset over here. So it does look like the firmware load might be over SPI. Neat. Let's see if we can get an image from it. Uh-huh. So can we communicate with it somehow, other than just loading the firmware? This has some pretty opaque parameters and commands here. List file and get file. This tool probably makes a lot more sense if you have their SDK documentation. But yeah, it looks like maybe this is also useful as a Linux interface for loading and storing files on an SD card that's connected directly to the camera. That's interesting though, I just don't know why they'd bother having USB and SPI for something like this for configuration. I mean, other than what we were just saying about saving money for the firmware, but that seems a little weird. Like, why wouldn't they just be able to send the firmware over USB also? I mean, a lot of devices have a USB mode where there's a basic bootloader. Maybe they just didn't want to have to implement that bootloader. Oh, that's better. Well, I think that might be approaching a good wrap-up point for this stream. It seems like there might be a few things to do in terms of, if you want to reverse engineer camera firmware or... Oh man, it's hard to resist just throwing the firmware into IDA and seeing what it looks like. I don't entirely know what CPU it is, though. It seems like it might be something with 16-bit opcodes like Thumb2, but I can't recognize Thumb2 off the top of my head, so we'd have to just try disassembling that probably. Let's maybe get that binary into a VM that has IDA. So let's take... Do I have a copy of these out here, just not organized? I think I deleted that. Oh, how did I end up rebooting that? Not quite sure how that ended up rebooting. This is slightly easier than extracting, or than copying the files out of the VM, probably. Oh, I see. It was courteous and didn't overwrite my existing directory, which is fine. So this is just giving us no directory structure, but I think we know what the names of the files are now, so we're fine. So we should see a 80 binary and those two firmwares. So let's just make a little directory for this. And I think I've got an IDA VM handy somewhere. While we're waiting for that VM, we could have a visual experience. Oops. This is the SPI mode firmware. Let's try the USB mode firmware. I'm slightly more interested in that. Anyway, that sounded like the VM booting. What is it trying to install? Oh right, this VM has like an ancient and very broken copy of SolidWorks in it for some reason. This must be really old. It's been a long time since I've even used SolidWorks. I need to put a less broken VM on my demo machine, clearly. Okay, let's get this in the VM. Okay, USB firmware. Let's make a bold guess that this might be thumb and see if that looks at all right, but I don't really think that's necessarily right. OVTF. This looks like maybe where the code is supposed to start. This does not look like it's gonna work. Yeah, I don't think this is the right architecture. Maybe it's 8-bit. You know, I also don't... I would think that maybe after all the time I've spent with 8051, I would recognize 8051 opcodes off the top of my head. I don't think this is 8051, but let's just try that. No, this is not looking good, is it? Ugh, yeah. What else might this be? I just want to look at the hex dump. This is about when it would be really nice to just have a database where people have compiled like common function prologues and epilogues in different architectures. See, you have these repeating patterns like this. Like, look at these F7 bytes. This looks to me like an 8-bit architecture. What other 8-bit architectures might people have used for a camera like this? There also sometimes are clues about the toolchain in the binary strings or other stuff that appears like at the end of the image. I think we don't need IDA at this point. Let's take a look at the difference between these two. Let's try doing this on one line. Usually I make separate files, but I'm getting some good suggestions to use bash tricks to do it in one line. SPI. Yeah. Let's try that without -y to see where the differences would be. This whole section starting at 14.080 is different. Plus all this. So this could give some clues about, like, for example, here's a section that just has a lot of differences, but then up here you can see some more isolated differences, which usually means that this is a jump target with some addresses that need to be fixed up. Or, I mean, there are a number of reasons why there might be addresses. It could be a jump, it could be data that's nearby, but typically these will be addresses for, like, functions that we're calling. And so, for example, looking through here, you can see this is 4b, this is 8b, which could be a function moving just a little bit. 4b, okay, so this might be an address, which is not aligned, but would be fine in an 8-bit processor. So maybe this is some kind of jump. Robert has some random guesses. Arc and extensa? Huh. Not quite familiar with those. Extensa I thought was like an FPGA processor. I'm not familiar at all with Arc. These seem higher end than what we'd be dealing with. So there's another tactic, which is to try to find out what kind of IP the company who makes these cameras might have licensed. Oh, okay. Extensa is the one that the ESP8266 uses. Interesting. I have not encountered anything other than the ESP8266 that uses this. But I'm pretty sure this is going to be 8-bit after looking at just the alignment of this stuff. And I mean, okay, check out this F728. This is going to be some common instruction sequence. Like this looks like some repetitive code in an 8-bit architecture is what that looks like. Sometimes you find people leave bits of like file system paths or other interesting hints as to what tool chain they're using. This firmware is small enough that maybe we wouldn't see that though. Oh yeah, we took a look at it with BinViz. I mean, I can show you BinViz again, but it didn't really look like that much to me. So this is, yeah, this is the OVTF image that we were just looking at. I mean, BinViz is telling us that, you know, like, so this is useful. Like, this shows us where the empty space is. It shows us kind of the structure. So, like, there's kind of a header. There's maybe, like, some bootloader interface stuff or interrupt vector stuff. Then there's, like, the beginning of the actual application at hex 1000. More empty space. There's some data down here. So, like, I think we saw strings in here. Yeah, those are the USB descriptors. Empty space. Then something else down here at 14,000. I don't know what this would be. Maybe a bootloader? It's kind of way off in the weeds and pretty near the end of the image, but also really small. And you'd think that if this was a bootloader that it might... Maybe they just configure the silicon really differently for webcams. So, I mean, I couldn't imagine them spinning different silicon for something like this versus a webcam, but maybe in a standalone webcam, the bootloader is actually designed to speak over USB, whereas this doesn't seem to have any USB descriptors in it. There's a lot of space reserved for a bootloader, which seems to be here a very, very tiny one. So maybe this version, it just bootstraps over SPI. Sensor not supported. So I guess this has to communicate with, I mean, the firmware on this OV780 chip is probably where they put pretty much all of the sensor-specific stuff. And then this chip is probably just a CPU with a bunch of special purpose peripherals to act as a pixel pipeline. Oh, well, which other architectures might this be? Oh yeah, and there's also a question about this. This is a pretty neat bash trick that, oh, I forget who mentioned this. Somebody mentioned this in stream recently. But I had been doing things where I hex dump files and sort them in separate files and then diff them. And this is a nice way to save a step. This has the shell. Like, I've seen this seems very similar to the, like if you're writing a make file, you can do something like $shell and then like xsd blah.bin. But in bash, then you could do something more like that, apparently. So yeah, apparently that actually replaces this whole thing with a file name, and in this case that's a devfd that points to the pipe that bash created. So bash will create the pipe in its process, then preserve it when it forks, and then the subprocess will be able to find it here in devfd. Which is pretty much a Linuxism. I don't know of other OSs that do this, but it's pretty handy. That's interesting. I wasn't expecting the current directory to be in there. That's interesting. I don't know where that would be coming from. Like maybe that's another file descriptor that only gets opened when ls is running in that shorter mode. I'm not quite sure what that would be. Oh, 4 is a directory. Maybe that's a file descriptor opened to the current directory? Interesting. Oh, Sodium mentions Plan 9 is capable of some sweet pipe shenanigans. That sounds true. I've never used Plan 9, but I would read about it, and it seemed like a really interesting operating system. I definitely took some inspiration for doing my own GUI subsystem from some of the stuff that they did. Hey, Tuke. All right. F728 is x86 for imol. That seems unlikely. Yeah, it seems really unlikely they'd be using x86 instructions on this thing. Do we have like a list of 8-bit CPUs somewhere? Or a list of... Oh, Duke's licking my elbow. That is the cutest. Oh, he's been in such a good mood since he's been hanging out on top of the rack. It's so warm up there for him. Like, this would need to be something that they could just license and stick in their chip, which probably means not anything from Texas Instruments. Maybe Renesas? I don't know if they do licensing. Probably not Atmel. Oh. Man, Tuco's just kind of rubbing around next to my legs like he wants to have some attention. They wouldn't have used like 6502 or Z80 or something like that, would they? Oh yeah, Ben's suggesting Z80 also. I guess I could try. I don't really know at all what Z80 or 6502 look like off the top of my head, but we could just ask Ida to disassemble it a few more times and see if that does anything useful. Alright, what else can we do? NEC, Renaissance. So we can do Z80. Can we do 6502? I don't know if this can do 6502. Might have to use a different disassembler if that's actually where they chose to take this. Oh, no, there's 6502. It's down there under Moss. And now my mouse is flaking out. Oh, the wireless here always breaks. I just need to have every single mouse receiver right next to the mouse. Yeah, I mean, this doesn't even have the address space, right? Let's see if any of this disassembles. Oh, this mouse, jeez. Yeah. That does not look real. Okay. Oh man, where's the receiver for this? I think it's plugged into the same USB hub that I should just unplug from all of this stuff that we're debugging. That's better actually. Maybe that was just the USB hub. Here I am blaming the electromagnetic spectrum when it could be USB's fault. No, I think it's actually the spectrum too. That's still crunchy. Oh, it looks like Sodium is running this in binwalk also and not seeing any of the opcodes that binwalk knows to recognize. Yeah, it could just be some kind of really weird CPU that they use and nobody else does. I don't know. I'd be really surprised if it was a Z80. Hey, boy. Huh, what? No. Apparently, random code turns into actually okay flow graphs in Z80 sometimes. This isn't real code, is it? This couldn't be real. Yeah, there's no way this is real code. Alright. Oh, Emily's asking if there's a copy of the file somewhere. I can't give you a copy, but I can show you how to download it. So the firmware we've been looking at is one of the particular versions that you can get off the D-Link website. So it's this DCS 933 version 1.13.05. And this is actually pretty much the same thing you can download from D-Link. So D-Link support website, DCS 933. Then if you get the previous firmware version, which is the one that we've been using, and download that, then that will give you this shiny DCS 933 Rev A firmware blah blah blah.zip, which will have a PDF which you can ignore, and this is the actual binary file which you would find on the SPI EEPROM. So if you run that through binwalk, you'll get exactly the same stuff I've been doing here. So specifically in a Linux VM, or apparently you're probably better off using Linux for this, because I guess CPIO on macOS is kind of nerfed. And I already shut down my Linux VM. But if you did something like binwalk-e, so it's, or not, let's see, dash lowercase e for extract, and then dash capital M for Matryoshka. Yeah. And then give that to your DCS whatever file, then you'll get exactly the same goodies that I'm playing with right here. So that's what I've got in here. And on macOS, it spews all the files into the same directory, but on Linux, it knows how to actually recreate this directory tree successfully. And then the interesting parts show up in, I think the firmware was in /bin, and the OV780 tool was in, or sorry, the firmware was in /sbin, and the tool was in /bin, I think. But then the pieces that you get from that firmware image just turn out to be these files. So OV780 is the actual app. There are some smaller apps for different OV chipsets, and then there are the two firmware images, which differ only a little bit. So I think that's pretty much what we've got. Tuco is just looking up at me like he wants to play, so maybe I'll try to play with him for a bit and answer any questions folks have. Hey, Tuco. Did you bring me a bolt, little dude? Where is it, little guy? I'm so bad at finding the bolts when the floor is covered in wires like this. Hey, buddy. there somewhere? There's a lot of bolts in here, but they're not the kind you like. What do you think, Tuka? Where? Do you just like wires? Do you just like wires? Do you see any bolts, Tuka? Just trash and wires? Alright, well the bolt fetching might have to be a work in progress here, since I don't think Tuco or I see a bolt at the moment. Alright, well, I think it's going to be some more effort to find Tuco what he desires. Careful, little guy. Oh, that wasn't the button I wanted. There we go. You went off? All right. Well, I hope you found that interesting. So just to wrap up, that was us finding a USB bus that goes between two chips on this webcam plus router contraption. And so many Tucos. How many Tucos can we get on the stream at once? So yeah, we found a USB interface that just went between these two chips on the same board and sliced it in half and connected it to a USB analyzer and to a computer and some individual devices. And so if we wanted to reverse engineer this particular camera or get more insight into how the camera is being set up by the firmware, then this might be a good starting point. It's also a technique that might be really useful for other devices. Like if there's some unknown device you want to reverse engineer and it just has an onboard USB connection, then this might be the ticket. Or if it's a system on chip that you want to do some more investigation on, but you're having trouble getting data in and out of it effectively, then this could be a way of giving yourself a USB port by stealing one from another on-chip device thing. Oh, Ross Oldfield in chat says, any clues looking in eMachine of the ELF header? I don't have an ELF header. So if you're talking about the actual, like the binaries here for Linux, like the OV780 tool, like that's going to be MIPS because that's what Linux is running on here. So yeah, these are all MIPS, but the actual firmware, so there are two processors here, well, at least two processors. There's the processor Linux is running on, which is the RT3352 system on chip. It has a 400 megahertz ARM core, or sorry, it has a 400 megahertz MIPS core, not an ARM, a MIPS, which is a little bit weird, but you still see these in router appliances not infrequently. So that's why we have these Linux MIPS binaries. But then these firmwares get loaded onto the camera chip, which is the OV780. And I don't know what processor architecture it is. We'd have to do some more digging to find out what that is. Well, thanks for tuning in, everyone. I will see you next time on the internet, and happy hacking.